In this in this lecture, we will study about the application of Gauss's law. And Gauss's law are very helpful to calculate the electric field when symmetrical body is available. So we will see some example of application of Gauss's law. Let's first start with the electric field due to a cylindrical long wire or a line charge outside the line charge. To calculate the electric field, first we take a cylinder of length L with axis coinciding with the axis of line charge. The linear charge density of line charge is given lambda. The charge enclosed by the Gaussian surface equals to lambda L. And Q in, that is charge enclosed, equals to lambda n, that is Q in equals to lambda L. According to Gauss's law, integration of E vector dot dA vector equal to Q into in by epsilon naught, or this imply E into 2 pi r into L cross surface area into 2 pi r L equals to lambda L by epsilon naught. Hence E equals to lambda L by 2 pi r L epsilon naught, or E equal to lambda by 2 epsilon naught r, that is E proportional to 1 by r. So electric field due to a linear charge will be given by this formula, lambda by 2 epsilon naught r at a distance r from the line charge. Next, electric field due to a solid cylindrical wire. Here it is shown a solid cylindrical wire. Inside the wire, we have to calculate the electric field inside the solid cylindrical wire. Here charge is distributed in the whole volume of the cylinder. Now linear charge density, that is volume charge density, is given, rho equal to volume charge density. And if we take a Gaussian surface, that is Gaussian cylinder, here again we are taking a Gaussian surface or which is a cylinder coaxial with the axis of the solid cylinder at a distance r, and the length of cylinder is L, and curved surface is at a distance r from the axis. Here charge enclosed by the Gaussian cylinder, this is Gaussian cylinder, will be given by volume of the cylinder, Gaussian cylinder volume charge density, that is Q in equals to pi r square into L into rho, because volume of cylinder is pi r square into L and density is volume charge density is rho. According to Gauss's law, phi net equal to Q in by epsilon naught. Now for this case, phi curved surface up, that is from this surface, phi curved surface down, that is from this surface, plus phi curved surface equal to Q enclosed by epsilon naught, that is for Gaussian surface, this is the up curved surface, cross section, this is the up cross section, this is the down cross section, and this is the curved surface. So electric field from this electric flux will be 0 from this surface, and similarly electric flux from this surface will be 0, but electric flux from the curved surface will be into 2 pi r L, because E is considered equivalent, that is equal at a distance r from the axis everywhere. So E into 2 pi r L equals to Now Q in is pi r square L into rho by epsilon naught. Hence E will be equals to pi r square L rho by 2 pi r L into epsilon naught, or equals to rho r by 2 epsilon naught, or equals to rho into r by 2 epsilon naught. That is proportional to r in this case. Next, a question. An electron is revolving around a cylindrical conductor of line linear charge density lambda. Find the kinetic energy of the electron. Here it is shown. Kinetic energy equal to 1 by 2 mv square. The centrifugal force required to rotate the electron is provided by electrostatic force between the electron and the line charge. Hence mv square by r equal to qe by e, or e equals to lambda by 2 epsilon naught r. This implies mv square equal to e lambda by 2 epsilon naught, or 1 by 2 mv square equals to e lambda by 4 pi epsilon naught. Hence kinetic energy will be 1 by 2 mv square equal to e lambda by 4 pi epsilon naught. Next, 4. Electric field due to plane sheet of charge or insulating plane or non-conducting plane. Here we are considering non-conducting or insulating plane. Again we take a cylindrical Gaussian cylinder and as shown in the figure, this is the cross-sectional area S, and it is also cross-sectional area, and this cylinder enclosed plane sheet of area. In this area it encloses the charge. Now charge enclosed by the Gaussian cylinder will be sigma into S, because only this charge is enclosed by this cylinder, and surface charge density is given of the plane sheet of charge. So Q in will be, that is Q in will be sigma into S. Only the this part of charge is enclosed by this Gaussian cylinder. So Q in will be equal to the charge enclosed by this charge available on this area. So we have written sigma into S, that is Q in equal to sigma S. Now according to Gauss's law, phi net equal to Q in by epsilon naught. Now phi curved surface left plus phi cross sectional area right plus phi curved surface equals to Q in by epsilon naught. Here phi CS cross sectional means this left side means this from flux through this area, and phi cross sectional right means flux through this area, and phi curved means flux through this curved part of cylinder, and it should not be net flux is equal to the Q enclosed by epsilon naught. So we can write now this flux will be ES because it is in the same direction. Again this will be ES because if we look from this side, electric field will be in this side because it is a plane sheet of charge. So ES plus 0. Now curve from the electric field from the curved surface will be 0 because electric field is in this direction, but surface area is perpendicular to electric field for the curved surface, so it will be 0 or C. Now putting the value Q equal to sigma S by epsilon naught, or 2 ES equal to sigma S by epsilon naught. Hence E will be sigma by 2 epsilon naught. So this is the formula for electric field due to a plane sheet of charge. Here it is to keep in the mind that our point is very near to the plane sheet of charge, then this formula will be applied. Next, 5. Electric field due to a conducting sheet of charge. Whenever the charge is given to the conductor, it resides on the outer surface of the conductor. So the charge is distributed both sides of the conductor sheet. Consider the distribution is uniform. Now surface charge density sigma is given. So and we have drawn a similarly a Gaussian cylinder enclosing this part of this uh, conductor sheet, and due to this conductor the electric field will be in this direction and here in this direction. Here Q enclosed will be 2 into Q dash because it is Q dash from because charge distributed in both sides. So from this side it is Q dash, again this because cross sectional area is same, so Q dash will be from this side also. So Q dash and Q dash, so Q in will be 2 Q dash equals to 2 sigma into S, because this area is given S. If this area is S, then this cross sectional area also will be S. So charge enclosed by the Gaussian cylinder is area enclosed by Gaussian surface or Gaussian cylinder into charge density. So this area is enclosed, this area, whole area is enclosed by the Gaussian cylinder. So area enclosed into charge density, so we have 2s into sigma. This is the charge enclosed by Gaussian cylinder, or that is Q equal to sigma 2 sigma into S. Now according to Gauss's law, phi net equal to Q in by epsilon naught. Now we calculate the phi naught. So phi cross sectional area left plus phi cross sectional area right plus phi curved surface, that is this is the flux through the this area, and this is the flux through the this area, and this is the flux phi curved surface means flux through this curved area. So we have this flux must should be Q enclosed by epsilon naught from the Gauss's law. Hence now flux through this area will be E into S, and flux through this area also will be E into S. So E into S and flux through curved surface will be 0 plus 2 sigma S by epsilon naught, or this implies 2 ES equals to 2 sigma S by epsilon naught, hence E will be sigma by epsilon naught. So when we have plane sheet of charge, electric field is sigma by 2 epsilon naught, and where we have plane sheet of conductor, plane sheet of conductor, then we have electric field equals to sigma by epsilon naught. We can also calculate this electric field from a plane sheet of conductor by another method. Here second method, we take the Gaussian cylinder such that it's one inch inside conductor. Here it is shown, we have one inch is inside the conductor and other inch is outside the conductor, and surface charge density is sigma and the cross sectional area is S. So according to Gauss's law, phi net equal to Q in by epsilon naught. Now this implies phi cross sectional left plus phi cross sectional right plus phi curved surface equals to Q in by epsilon naught. Here it is because this end of Gaussian cylinder is inside the conductor, and we know that inside the conductor always electric field is 0. So E into S will be 0. So flux of this flux through this area will be 0. So phi cross sectional left will be 0 from this area 0. Now only we have flux through only this area, this cross sectional area, and which is equal to E into S. If electric field is E, then E into S. Again from curved surface is 0 because electric field is in this direction and area is always perpendicular to the electric field for the curved surface. So we have sigma S by epsilon naught, hence E equal to sigma by epsilon naught. Phi CS left E into S equal to 0 into S 0, since inside the conductor electric field is 0. CS equal to represent cross sectional area. Next question. From figure, find the angle theta for the equilibrium of the charged sphere. If A, the sheet is conducting, do the sheet is insulating. The first case is our the sheet is conducting. So we know that electric field due to a plane conducting sheet near to the surface is given by sigma by epsilon naught, and it is always perpendicular to the area of sheet. So in this case, electric field at this charge will be in this direction, and its value will be sigma by epsilon naught. Hence force on this charge will be F equal to QE, or sigma Q by epsilon naught. Now if we draw the free body diagram of this body, then we have tension in this direction, weight in this direction, and electric force in this direction. Taking component of tension, T cos theta will be in this direction and T sin theta will be in this direction. Now this spherical ball is in equilibrium, so we can write T sin theta equal to Fe, that is this force equal to this force, or equals to sigma Q by epsilon naught. And T cos theta equal to mg. Hence tan theta will be sigma Q by epsilon naught by mg, or sigma Q by epsilon naught mg. This implies theta equal to tan inverse sigma Q by epsilon naught mg. So this is the angle made by a string connected to the ball, to the surface. Now in the second case, the sheet is insulating, and we know that the insulating sheet have electric field given by sigma by 2 epsilon naught. Hence Fe on the body will be Q into E, or Q sigma by 2 epsilon naught. Again tan theta QE by 2 epsilon naught, Q sigma by 2 epsilon naught by mg, or sigma Q by 2 epsilon naught mg. That is theta is equal to tan inverse sigma Q by 2 epsilon naught mg. Next, in the above problem, if a sphere is displaced slightly and released, find the period of oscillation. Here solution will be, we know that in such type of case, T equals to 2 pi root under L by G effective, and now acceleration due to electric field is sigma Q by m epsilon naught, and acceleration due to gravity is G, which is here shown. So G effective will be in this direction. That is vector sum of these two accelerations. So G effective under root sigma Q by m epsilon naught into ka whole square plus G squares, and putting this value we get the time of oscillation. So hence T will be equal to 2 pi under root L by under root sigma Q by m epsilon naught to the whole square plus G square. In the second case, A equal to sigma Q by 2 m epsilon naught, or AG equal to G, hence T equal to 2 pi under root L by G effective, or 2 pi under root L by sigma Q by 2 m epsilon naught to the whole square plus G square answer.